Okay, thanks very much. So I wasn't the alpha, but I am the omega of the talks here for this session. So yeah, I'm back to CubeSats again. So, yesterday I talked about trying to do actually a small sat to take it to the moon. So that's a pretty ambitious project there. So today I'm going to talk about actually putting a small optical telescope in orbit on a CubeSat and making that data available to non-professional organizations like the folks here in the room. So kind of formed another team and got for team members here, Kevin France, who's professor at the University of Colorado up at Boulder. He's with currently, he's put up a CubeSat, and I'll talk about that in just a second. Optical UV CubeSat, talk about that in a second. Dr. John Martin here, of course, part of SAS. Ken Spencer here is with the Astronomy Association there in Arizona, where this project really originated from. Dirk Terrell, I think you've heard of him. I roped him back into this project here for the optical CubeSat. So, okay, so outline again, I spent about 20 years with Lockheed Martin. Every time you went to do a presentation there, you had to do an outline. So that's just a habit or whatever. So I'll give you the basis for why we're wanting to try to do this. There's a couple of current CubeSat projects dealing with the UV realm in space. I'll talk about those. They have a short lifetime. And then I'll talk about what we're planning. Whoops, I hit the wrong button here. Talk about what we're planning to do here, objectives of the system, just a little bit of information on the design of it itself. It's still pretty far in the future. Of course, you got to have funding sources and then actually opportunities for participations for, again, non-professional observers and such there. So this project also came out of this Astronomy Association in Arizona. I was telling you a story yesterday on joining them. We started with the lunar project. That was too complicated, too costly. We said, let's do a small telescope in Earth orbit. So I did the engineering analysis, wrote a white paper for them. I got up and said, okay, guys, I need like $5-6 million. Handed it over to the directors of the association, said, you go find the funding and we'll move it forward. So it stalled right then, right? And it wasn't until it flipped over to my current employer that we actually got it going again. So, okay. Let's see. Okay. Why do we need a ultraviolet observatory? Well, there's a large portion of the spectrum we just can't see from the ground, right? You can't really do UV observations from the ground. You can get a little bit of it, but not really. You got to do it in a space environment, okay, outside the atmosphere. There's only a few missions currently up there now that actually do UV, right? I mean, Hubble's up there, obviously, but it's, coming into life. Gala, they cover a portion of the spectral range there, but we're getting ready to go into a gap where we're not going to have any on-orbit UV type observations available. Whoa, okay, we've had this problem again. Okay, this is where it was, yep. So the UV research field is sparsely addressed, but it's very important for the scientific community. And there I mentioned we're entering this gap here, where it's about a 15-year gap. We're not going to have any type of capability in orbit to observe in the UV spectrum. So, and, NASA has this UV optical IR surveyor system that they're planning to come online. Of course, everything they do keeps slipping out, right? It was 2035. The latest I've been informed of is it's like early 2040s, 2040 at the earliest, right? So, all right, talked about CubeSats a little bit yesterday. They were devised, like I think I looked it up last night, back to 1999 by a couple of professors, Cal Poly State Tech and from Stanford. So they're based on this uniform, again, size of a cube, 10 by 10 by 10 centimeters, a little over about 3 pounds, 1 1/4 or 1 1/3 kilograms. And so you build these things up, right? So there's a 1U there. You build these things up. This is typically the largest that you can do a NASA ride share. And I mentioned that yesterday. The break point between CubeSats and small sats is like 27U or so. And so again, going back to yesterday, I really don't think I can get a SAR on a CubeSat. It's going to move into the small sat range. Typically what people have launched is like generally the 3U range, okay? So you've got colleges now that put up CubeSats as experiments. You've had high school groups and stuff do it. So it's all built again on this 1U type. So NASA supports CubeSats very much so. There's a whole website. If you go off, I think, yeah, here's the resource right here. You go hit that link. They've got a whole document that's developed for educational organizations, again, colleges, whatever that want to, develop a CubeSat and try to launch it. There's this thing called Launch Initiative that, again, you can do what they call the ride share with the launch vehicle in the orbit, right? So you have to propose this and then be accepted. And they have a whole outline saying, well, you should have everything lined up before you even propose, because if we accept you as being on one of the ride shares, we expect you to show up at the integration point, before they get ready to launch this thing. So they don't want you to, stump your toe anywhere. So you're supposed to have all your funding and everything lined up before we ever go apply for one of these launch initiatives. So, and typically what they launch is 3 and 6 use CubeSats. They do take up to 12, okay? All right, so a couple of missions are up there. This one, the Colorado Space Telescope Project, or CUTE, everybody has to have a name, right? Okay, I've got one just a second, so hang on there, right? So this is by University of Colorado up there at Boulder. So Kevin France is the principal investigator on this. It's a 6U system, okay? It's a UV type system designed to look for exoplanet atmospheres, host stars and such. It launched back in October this last year. So it launched up, October, went through the commissioning, shakedown portion of the mission here through the end of the year. First part of this year, it actually started conducting science operations. Haven't talked to Kevin since it actually started science operations, but one of the reasons I contacted him, because I wanted to try to take advantage of his experience and see if he wouldn't be interested in a follow-on mission, which we're proposing. So this is designed for like a 2-year mission. We just got through hearing from the professor at ASU. They have this thing called Sparks, right? Another cutesy name there. So this one's a spectroscopy type mission. 10 centimeter telescope, reflective telescope. It hasn't launched yet. It's supposed to be launching into this year, okay? So I think this is like a 1-year mission. This is a 2-year mission, so it's already up there. So it's going to run out in a couple of years, okay? Okay, so what we're proposing through my company here is a follow-on UV optical system, okay? So I've called it the Ultraviolet Follow-on Observatory, or UFO. That's my name. I want to go there, right? So, okay, so told you about that gap between these previous 2 missions. Even if they're successful and they get extended for a year or so, they're going to end in 2025, 2026, something like that. Between there and 2040, when the NASA system comes on, you've got this gap, with Hubble coming offline and such, of no actually active systems in space, okay? So what we're proposing is a constellation of 4 CubeSats, okay? So we'll develop one as a prototype, launch that, and the timeline for these systems were about 5 years, okay? So I'm trying to extend the reliability of these systems from just a couple to like 5 years. So I was like the reliability engineer for NASA, for the Lockheed Center there for 5 or 6 years. So I'm going to really put in play my reliability engineering to try to get these systems back up. So 4 overlapping CubeSats, each one running about 4 to 5 years lifetime, high Earth orbit somewhere around 700 kilometers. And we want to design it where it's simultaneously going to image in both the UV and optical. So we want to bring the signal in, do a dichromatic split on it, have a camera capture the UV portion of the spectrum which you're looking at, and another camera capture the capture the optical, right? So UV portion about 240 to 390 nanometers, and of course the optical is the standard 400 to about 750 or whatever. So I'm proposing this not to try to compete with these two guys that are going up, right, but to be a follow-on support mission from them. So here's one thing, you know, kind of something similar to this. This probably won't look exactly like that, but these things typically look like solar panels unfold, very small. This one, and I'm proposing, is a 12U, not a 6U, so it's doubling the size of the two ones that are up there. Components of it typically look something like this. You got about a third of the system. It's got the electronics, a third of the system that has like for reaction control wheels and power and stuff like that. And you got about a third of the system for your payload on there. So for why do we want to go for a 12U? Well, you know, there's this company called Aperture Optical Sciences. They build telescopes to go in satellites and such. So they have a lot of military contacts. Talked to them several times. They have two standard type optical telescopes. They have an 85 millimeter and then a 250. So that you can't get a 250 on a 6U. And I really didn't want to go with 85. So I'm going to push it to see if we can't go for a 12U, which will take then a 250 millimeter telescope. So there again, you know, the design is to try to take the signal in, break it out, and then we have the two separate cameras where we can collect simultaneous measurements in both the UV and the optical. So I've been talking to this company here. Let's see, the 85 millimeter telescope, I think, has a standard cost of, if I remember now, 150 grand. The 250, something like $250,000, 300, something like that. You think a lot of money. It is, but they're space qualified. So objectives for the project, we're going to be doing the design to take the system engineering design. We're going to do something what they call a model-based system engineering formalized approach. That's something that my company has been pushing. You know, typically if you go back to the general, if you know about system engineering flow, you go through system requirements analysis, you do preliminary design, you do critical design, you have design reviews in there. It's a waterfall type approach. Well, you get all the way down to the detailed designs, you start making changes and stuff. All your system requirements are in documents and stuff that are lost somewhere where they're not updated, right? So this model-based system engineering approach is basically you're building a digital model of your whole system, and you take everything with you through the whole design process. So if you make changes back here in the critical design, those changes are folded back up and affect what's going on with your higher level designs and requirements on it. So at the end, you have a complete, you know, integrated design package together. So there's certain tools and stuff that you utilize to do that. We are utilizing there at PSG. I think maybe I'm saying all this right here. Yeah, later life cycles. So engineering, so we got engineering objectives, science objectives, right? Already talked about this. Simultaneous space-based observational data. Again, the UV range, the optical range, duty cycle, about half an orbit, a little more half an orbit. So we're thinking, you know, these are just preliminary calculations up front, right? Dwell time on specific targets, maybe 35 minutes per orbit. Orbit mission lifetime, about 5 years, somewhere in that. Try to get a system reliability of 2 nines, system availability of 4 nines, to give you half orbit utilization. It's funny because you go back to the Lunar HMAP project we talked about yesterday, that ASU is sending to the moon. I actually interviewed with them for a project management role a couple of years ago, whatever. I walked in there, I said, well, what's your system reliability spec that you're getting ready on the system? And they said, well, we don't have one. You know, we expect it probably to fail when we launch the thing. I was like, are you seriously, really? I mean, you will go in there with the expecting to fail. So again, coming from a reliability standpoint, I'm putting these numbers here to try to achieve. Now, when we get into the actual design stage, right, it goes back to the system modeling approach. We actually get into that design stage. We have to work with vendors, see if they can actually achieve that or not, right? Educational directives. So we're trying to design this thing to tie in very closely and heavily with educational prospects from not only K through 12. We want to expose students to astronomy, space flight, community colleges, university level objectives here. We want to provide, so the data we hope to provide to university faculty, professional astronomers, like John sitting here. Also semi-professional observatories and stuff. I just want to make a comment about sitting here, listening to the talks earlier today and such. I've been coming to this conference probably for, I was thinking, around 15 years or so. Not consistently, but if you go back 15 years when I first started, and the quality of research work when I first started to where we are now is just really impressive. I mean, listening to what the earlier talks, both these days, it's the same as, professional. You're not being paid, right, to do your research work, but it's just as good as any professional astronomers I can see. So you can applaud yourself for that, right? So objectives again, educational, try to get the data available to not only community colleges, but also to organizations like this, okay? So you could actually get time on a system, because I mean, here, we can't get time on a orbiting telescope, right? You're never going to get time on Hubble, right? Or one of the other even smaller telescopes from those universities. They own the time on that. They're going to have what they have their priorities set such, right? So the objective of this program is to try to make the system available to a wider audience. And general public, public objectives, right? Try to use this project, try to get information out to the general public, astronomy, science, STEM, the Astronomy Association. That's where they come in. They've got plans in there to actually go out and promote this, and some of their star parties and stuff they do, along with the Lunar SAR project. So I went through and did a cost analysis, just trying to say, okay, what cost benefit can we get from this, right? So I went back and I just took some public information I could find online. And like, if you take the HST, right? So I went back and it's like, so that's $16 billion or so. If you go all the way back to first design operations currently, and what they've spent on that. And I found it's been about 18,000 peer-reviewed published papers based on Hubble data. So if you just take that ratio, these are in thousands, right? So you got about $889,000 for each public or each peer-reviewed published paper that's come out based on Hubble Space Telescope. So Las Cruces Observatory, that's a nonprofit private observatory, but they have it set up to where you can go in and buy time on that. And there's a series of observatories around the Earth there. They have a public or published papers based on that. So these are public numbers, or took off the web. So if you look at that and divide out that ratio there, you get about $102,000 per peer-reviewed published paper from that observatory. So what I'm estimating here, these numbers, I just come up with some numbers here, right? For the 1 and 2 here for our program. So number 1 is yearly operational cost at 1.5 FTE. Well, let's go to number 2 here. So total cost of the system, I'm saying about 4.5, 5 million for the prototype, 1 million for each additional CubeSat. Over the lifetime of about 16, 17 years, I've got about 22.7 million, averages out about 1.34 per year. So if I get out of this information, if we get 3/4 of the percentage of papers to be published that we had under LCO here, we can come up with about ratio of $13,000 to $20,000 per peer-reviewed published paper. So I'm trying to show that cost-effective wise, we can get data from a observing Earth orbiting observatory there a lot more cost-effective than the other systems out there. So I mentioned this Las Cruces Observatory. It's a network currently of observatories around the world. So they already have set up a system where you can go in there online and request time on a target and such, right? And it prioritizes it. It sets everything up for you. It goes out, selects a telescope, collects the data, sends the data back to you, right? So that's already set up a system wide. So I'm hoping to be able to talk to them to plug into that system of what we want to do. So you get online, same thing, find your selection of targets you want to collect data on. It will prioritize it, send it off, and it goes up to the a ground station system. Let's see. So yeah, I want UFO to be part of LCO. It goes up to the ground station command and control system, which Amazon Web Services now have a ground station fully managed. You can go off there and you can buy time on that, and it sends up, it'll take care of your command and control to a satellite in space. So, because before you'd have to either build your own command and control system, right? Or you'd have to buy time from one of the NASA systems or something like that. Well, now, AWS does that for you. And it's very cost effective. I looked into that. Direct access to their services and infrastructure. You just buy the time off of it. So we've got the ground station control portion solved. If I can take that and tie that in with LCO, I've got the prioritization and the upfront queuing solved, right? So all I need now is the satellite, right? Partners, talked about this before. I'm with this Prime Solution Group out of Phoenix. Astronomy Association of Arizona. They're going to be taking care of the education part and the public part there. I've got Kevin France again, from University of Colorado. He's built the Cute satellite. They had Blue Canyon Technologies, which is a commercial company to build CubeSats. They built the Cute. Kevin said he's not sure he'd go back to them again, so it's going to be discussion there. So I got John here with the University of Illinois. He's going to be a heavy user of that, and then Dr. Terrell there at Southwest Research Institute. He has a lot of his scientific research work is in ultraviolet targets and stuff, in globular clusters and such. So project schedule, I have to go after funding here. So that proposal is due in the November timeframe. So there's 3 or 4 months award. So say we get awarded that would be early spring, February, March next year. This is just a typical time frame that NASA had on their website there. So I don't know if this would actually work. We've got the concept. They run out here about a year or so. So say it takes 1.5 years, 2 years to get the system up, get to a launch point. So let's see, next spring is 23. So that'd be 2025. We'd get up there about the time the Cute and the Spark system would start winding down to try to fill that gap. That's the plan and the approach. So funding for this is the Astrophysics Research Analysis Program. Target for that one there. So it awards up to 4 years duration, $5 million, I think, is the cap. So we got to keep everything under about 5 million, but then you can get extension funding there for operations and such. So 2022 is when we're talking about funding. So opportunities for participation, like I'm saying here, we know this, right? We know this too. So again, we're designing this whole project to be able to reach out and provide opportunities for pro-am type astronomy research, okay? For just like this organization, right? So I'm hoping that SAS will be interested, involved in this, AAVSO, whatever, other organizations that might want to take advantage of the system. We haven't talked about splitting a time or whatever, because we'll have to have some of the time for the professionals, right? That, are contributing to this. University and stuff, they want their time on the system, but I'm hoping to at least have half the time or more dedicated to high-end amateurs to come in and supplement your research work. So, okay, I think that was it. We're planning on doing there. We'll see. I can report next year if we actually got the project underway or not.
All right, let's go with the online question first.
I need to scroll back up. There are a few on now. So Tom Smith says, how much volume does the CubeSat high gain antenna take up?
Volume on as far as inside the CubeSat structure?
Yeah, he says he's read an article about 3D printing the parabolic high gain antenna in space after launch.
Oh, actually 3D printing it in space after you launch? Okay. Maybe.
Is it a major constraint for us, I think is what he's asking.
No, I don't think it's a major constraint. You know, I mean, we were talking about going to the moon yesterday. There you got to have like, you know, larger power source. You got to have tracking because you can't use GPS. Earth orbit here, we don't have those same type of problems. So
should I go to the next one?
So Stan Watson, I just have a comment actually.
Okay.
I'm a biologist. That's how I pay for my telescopes. But basically your financial analysis seems very much on target for a mega scale biology project in terms of costs per publication. You're being optimistic. We now professionally look at somewhere between $50,000 and $75,000 per paper. So okay. You're in the ballpark. I would be a little more pessimistic about the money.
Okay. All right. Well, thank you. It's good to know. So.
Yeah. How can you have your availability 100 times better than your reliability?
Okay. Where was the question coming from? Oh, sorry. Yeah.
How can your availability be 100 times better than your reliability?
Well, your availability, let's see, I'm trying to remember those definitions from your guys. Availability is your available uptime over downtime, right? So you can have a high reliability of your system, but not have it available as much as you wanted it to. So, 4 nines actually, I mean, for a ground station, you usually target 6 nines for availability, but 4 nines would be, you know, what is out every 1,000 or 10,000 hours, you know, you're down a few hours there, or offline where you can't collect data. So you have to have, you know, your availability is always higher number than your reliability numbers when you're producing those systems. So,
when it doesn't work.
What's that?
It's available when it doesn't work.
Well, that's a pessimistic way of looking at it.
Well,
availability is getting at things like scheduled maintenance.
Yeah, I mean, you know, availability is like when you want to use it, it's available, right? You know, so maybe your reliability says it's going to be, and the 0.29s is like it's down 1 hour every 100 hours or whatever, but availability might be it's only you've only got half an orbit time frame that you can collect data because you're on the sun portion of the Earth and stuff. So you want it to be available when you can collect data a higher amount of time than the reliability would have the system up. So if that makes any sense. So, okay.
Just an observation on the budgetary numbers. Many, many years ago, I had an office next to Helmut Abt when he was editor of the Astrophysical Journal. And I distinctly remember him opining that refereed journals in astronomy were typically read by 3 astronomers. And I was looking at the numbers you had for the Hubble Space Telescope. If you extrapolated that, it's $275,000 per paper per reader. I'm just trying to visualize how much science you could do for just removing one reader from a list of journals.
Expensive numbers.
Let me do one of the online ones while the microphone gets to the back. So Nick Dunkel asks, how will the satellite be stabilized to permit the telescope to stay on target?
Yeah, there was some question, and we actually worked that question before about stabilization and jitter and stuff on the target. So there's either 2 ways: you either have reaction wheels on your satellite, or you have to use some kind of RCS type system. But it's that question has been worked, and we think that it's solvable for what we want.
I'll add in, Nick, that part of the deal then becomes your choice of pixel size on your detector, and basically keeping the jitter inside the pixel.
Yes.
So my question is, how would the time allocation committee, the TAC, work? How would you envision that would work here? And I also bring up the point that when Hubble had time available for amateurs, it never really happened because the amateurs couldn't properly fill out a proposal. Proposals were quite complicated. How would that all work?
I haven't thought through all that process yet. I would think I was thinking of something similar to you want it as complicated as professionals, right? But you want some kind of review process, whatever. So if there's an overabundance of which there probably will be, of time requested, they would prioritize that. Maybe it's based on peers, your peers or whatever, saying these are the important projects. Like I'm thinking through this morning, like it seemed like very important to look at the spectroscopy and photometry of these flaring stars. So maybe that rises up to the top of the priority list and stuff, and you would rank the priorities based on something.
What do you envision that being an amateur organization, or do you envision there's going to be some kind of larger governmental or some type of privately financed organization controlling the telescope?
I would like it to be a nonprofit, kind of like the Las Cumbres Observatory system is. Keep the government out of it as much as we can. We know how well the government works, right? So amateurs running that, I would think it'd be great if we have a combination of amateurs and selected university level type organization that would look at the prioritization and importance of whatever projects you're trying to image. So.
Well, we have another online one, but I'll also say that you look at LCO and we see students here given posters on data they got from LCO, and so I think that's what Doug's talking about envisioning as far as being able to.
Right.
Yeah. Let's see. Dennis Conti asks, what specific science case do you foresee taking advantage of the simultaneous UV and optical observations? Are there any constraints on what parts of this? Well, that's the second part. Let's do the first part.
Okay. So what was the first part?
The first part was what specific science cases do you foresee taking advantage of the simultaneous UV and optical observations?
I would think that would be an advantage of the view in both the portions of the spectrum for these high type energetic objects that,
I remember me and Dirk Terrell on that Zoom, and in about 5 minutes, we had about half a dozen or 2 or 3 dozen ideas. I'll spit out some of them. ISM, star cluster work, follow on with cute solar system objects, including outer planet observations,
Venus observations.
Yeah, and Venus, and yeah.
I listed those in the paper that's in the document.
There are a lot of good, bright target projects.
Yeah, there's a whole list I put in the paper inside the.
It's in the paper. I should do a second part of the question. Are there any constraints on what parts of the celestial sphere will be viewable? I
haven't thought through that yet. So.
I guess it'd be like the Hubble Space Telescope, that you can't see through the Earth or look at the sun.
True. Yeah.
But otherwise, you go around the Earth, so you see all of it at least once.
And that kind of depends on orbital altitude and inclination, all that, which we need to figure out when we get into the mission requirements. So all that up front, system engineering, science mission requirements is where all that information would be hammered out. So.
Do you plan on having any dedicated background projects? So if you don't have requests, you have something to fill the time?
Oh, I'm sure there'd be a list of, and like the backlog or whatever, or projects that, if there's a slot of time, it would immediately go down there and pick off whatever it is that's sitting there and queue up the satellite to image that. So.
I'll point out that James Jackman has put in, and I should have mentioned this among the possibilities, simultaneous swift tests and ground-based observations of flares our team has been doing would be a perfect example where such an instrument will be good. Yeah, because the UV for the flares, right, guys? Yeah.
Okay, there we go. Yeah.
All right, any more questions? Looks like we covered it. Thank you so much, Doug.
All right, thank you.